Welcome back to Science with Sleepy. Tonight we're exploring a question that mixes legend with real science. What would it actually take for Santa's sleigh to work? Picture Christmas Eve. Children are sleeping. According to the story, Santa Claus visits every home with children. He delivers presents. He does it all in one night. But here's what makes this interesting. This isn't just a story, it's a real physics problem. It's an engineering challenge. It's a puzzle that touches on fundamental questions in science. How fast would Santa need to travel? How would a sleigh actually fly? What would reindeer need to do? How much energy would be required? What materials would survive? These questions have real answers. Let's find them. This question has fascinated scientists and engineers for decades. It's appeared in scientific journals. It's been analyzed by physicists. It's been calculated by mathematicians. And every time someone digs into the numbers, they discover something remarkable. The scale of the challenge is almost beyond human comprehension, but by breaking it down, by examining each piece, we can understand what would actually be required. The legend of Santa Claus has evolved over centuries. The modern version, with flying reindeer and a sleigh, emerged in the 19th century. But the physics behind this legend, that's timeless. The laws of motion don't care about stories. They apply equally to Santa's sleigh and to a commercial airliner. So when we ask what it would take, we're really asking, what do the fundamental laws of physics tell us is possible? First, we need to understand the challenge. What exactly is Santa trying to do? The answer seems simple, but when we break it down into numbers, the scale becomes almost impossible to imagine. Let's start with the basics. Santa needs to visit every home with children. But how many homes is that? How many children? How much time does he have? According to the United Nations, there are about 2.2 billion children under 18 in the world. That's 2,200,000,000 children. Think about that number, 2.2 billion. To put this in perspective, imagine if you could count one child per second. It would take you about 70 years to count them all. That's longer than most human lifetimes. And Santa needs to visit each one, not just count them. But Santa doesn't visit individual children. He visits homes. So how many homes have children? This is trickier. Families vary in size. Some homes have one child. Some have 5. Some have none. If we assume an average of about 2 children per home with children, that gives us roughly 1.1 billion homes to visit. 1.1 billion homes. The distribution of these homes is far from uniform. In dense urban areas like Tokyo or New York City, you might find thousands of homes per square kilometer. In rural areas like the Australian outback or the Canadian tundra, homes might be separated by hundreds of kilometers. This uneven distribution makes Santa's route planning incredibly complex. He can't just fly in a straight line. He needs to zigzag across continents, darting between cities and rural areas, optimizing his path constantly. Now let's think about time. Santa has one night. But what does one night actually mean? Earth is a sphere. It rotates on its axis. When it's night in one place, it's day in another. So Santa doesn't have just one night. He has multiple nights, one after another, as he follows the darkness around the planet. But even with this trick, time is limited. Let's say Santa starts at the international dateline, where Christmas Eve begins. He follows the night westward, visiting homes as darkness falls. But he can't take too long at each home. If he spends even 1 minute at each home, that's 1.1 billion minutes. That's about 18 million hours. That's about 750,000 days. That's over 2,000 years. So Santa clearly can't spend a minute at each home. He needs to move much faster. He needs to spend seconds, not minutes, at each location, but even seconds add up. If he spends just 1 second at each home, that's 1.1 billion seconds. That's about 18 million minutes. That's about 305,000 hours. That's about 12,700 days. That's about 35 years. So 1 second per home is still too slow. Santa needs to move incredibly fast. He needs to spend fractions of a second at each home. He needs to travel between homes at speeds that are hard to imagine. But wait, there's another factor. The distance between homes. Santa doesn't just need to visit homes quickly, he needs to travel between them. And homes aren't evenly distributed. Some areas have many homes close together, like cities. Other areas have homes spread far apart, like rural regions. The average distance between homes varies dramatically. In a dense city, homes might be just meters apart. In rural areas, they might be kilometers apart. Across the entire planet, if we spread 1.1 billion homes evenly, each home would occupy about 0.045 square kilometers. That means the average distance between homes would be about 210 meters, or roughly 700 feet. The distribution of homes creates a fascinating optimization problem. In Manhattan, homes are packed incredibly densely. A single city block might contain hundreds of apartments. Santa could visit dozens of homes in seconds. But then he'd need to travel to the next city, which might be thousands of kilometers away. The challenge is finding the optimal route that minimizes total travel time, while ensuring every home is visited. But this is just an average. In reality, Santa would need to travel much longer distances in rural areas, and shorter distances in cities. The total distance he'd need to cover depends on his route. If he could visit homes in the most efficient order, following an optimized path, he might need to travel roughly the circumference of Earth, several times over. Consider the logistics of visiting a city like Tokyo, with its 37 million people. If we assume an average of 2 children per home, that's about 18.5 million homes in the greater Tokyo area. If Santa could visit these homes efficiently, staying within the city, he might cover them in a relatively small geographic area. But then, he'd need to travel to the next major population center, which could be thousands of kilometers away. The trade-off between dense clusters and sparse rural areas is a key challenge in route optimization. Earth's circumference is about 40,000 kilometers or 25,000 miles. If Santa needs to visit 1.1 billion homes, and the average distance between consecutive homes in an optimized route is, say, 500 meters, then his total travel distance would be about 550 million kilometers. That's about 13,750 times around Earth. That's about 1,375 times the distance to the Moon. So Santa needs to travel 550 million kilometers in one night. But how long is one night? If we're generous and say Santa has 24 hours total, following the night around the planet, then he needs to travel 550 million kilometers in 24 hours. That's about 23 million kilometers per hour. That's about 6,400 kilometers per second. That's about 21,000 times the speed of sound. The speed of sound is about 343 meters per second, or about 1,235 kilometers per hour. Santa would need to travel at speeds that are thousands of times faster than sound. This is approaching a significant fraction of the speed of light, which is about 300,000 kilometers per second. Santa would need to travel at about 2% of the speed of light. To understand what this means, let's compare it to familiar speeds. A commercial airliner cruises at about 900 kilometers per hour. A bullet from a rifle travels at about 1,000 meters per second. or about 3,600 kilometers per hour. The International Space Station orbits Earth at about 27,600 kilometers per hour. Santa would need to travel about 850 times faster than the space station. These numbers are staggering. They're almost beyond comprehension. But they tell us something important. The challenge isn't just difficult. It's approaching the limits of what physics allows. At these speeds, strange things happen. Time dilates. Space contracts. The laws of physics as we know them start to behave differently. At 2% of light speed, these relativistic effects are small but measurable. If Santa traveled at this speed for an hour, his clock would run about 0.003% slower than clocks on Earth. Over the course of his entire journey, this time dilation would save him about 2.6 seconds. That's not much, but it's real. It's a measurable effect of Einstein's theory of relativity. But before we dive into those deep waters, let's think about another possibility. What if Santa isn't alone? What if there are multiple Santas? What if the work is divided? This is an interesting thought. If we had, say, 10 Santas, each would only need to travel 1/10 the distance. If we had 100 Santas, each would only need to travel 1/100th the distance. This doesn't solve all the problems, but it does make them more manageable. Instead of one Santa traveling at impossible speeds, we could have many Santas traveling at merely extraordinary speeds. This is a solution we'll explore more deeply later. But for now, let's understand the full scope of the challenge. The challenge breaks down into several key problems. First, there's the speed problem. Santa needs to travel incredibly fast. Second, there's the flight problem. A sleigh needs to actually fly, which requires lift and propulsion. Third, there's the reindeer problem. The reindeer need to provide power, which has biological limits. Fourth, there's the energy problem. Moving this fast requires enormous amounts of energy. Fifth, there's the materials problem. The sleigh needs to survive these extreme conditions. And sixth, there's the logistics problem. Santa needs to find every home, navigate efficiently and deliver the right presents. Each of these problems is fascinating on its own. Each touches on deep questions in physics, biology and engineering, and each has solutions that are, in their own way, impossible. But that's what makes this question so interesting. By exploring the impossible, we learn about the possible. By pushing against the limits, we understand where those limits are. So as we continue this journey, keep in mind that we're not trying to prove that Santa is impossible. We're trying to understand what would be needed to make him possible. We're exploring the science behind the legend. We're discovering what physics, biology, and engineering would need to accomplish. And in doing so, we're learning something profound about the universe we live in, and the limits that shape it. The challenge is enormous. The requirements are extreme. But that's what makes it worth exploring. So let's begin with the first and most obvious problem: speed. How fast would Santa actually need to travel? Speed is perhaps the most obvious challenge facing Santa. He needs to visit billions of homes in one night. That means he needs to move incredibly fast. But how fast? Let's do the math, step by step, and see what the numbers tell us. We've already established some basics. There are about 1.1 billion homes to visit. Santa has roughly 24 hours if he follows the night around the planet. But we need to be more precise. How much time does he actually have? Let's think about this carefully. Santa starts at the international dateline, where Christmas Eve begins. As Earth rotates, night falls in different places at different times. Santa follows this night, moving westward, staying in the darkness. But he can't take the full 24 hours, because he needs to finish before sunrise catches up with him. In reality, Santa might have closer to 31 hours total, if we account for the fact that he can start in the earliest time zones and finish in the latest ones. But let's be conservative and say he has 24 hours. That's 86,400 seconds. If Santa needs to visit 1.1 billion homes in 86,400 seconds, and if we assume he spends 0 time at each home, just passing through instantly, then he needs to visit about 12,700 homes per second. That's 12,700 homes every single second. Think about that. In the time it takes you to blink, Santa would need to visit thousands of homes. Let's break this down further. If Santa visits 12,700 homes per second, that means he spends about 0.00079 seconds at each home. That's 79 microseconds. In that time, light travels about 24 kilometers. A human nerve impulse travels about 0.08 millimeters. There's simply no time for Santa to do anything meaningful at each home. He couldn't even perceive the home, let alone deliver presents. This tells us something crucial. At these speeds, Santa wouldn't be stopping at homes at all. He'd be moving so fast that the concept of stopping becomes meaningless. He'd need some form of automated delivery system that could drop presents as he passes by, without him ever slowing down. But of course, Santa can't spend 0 time at each home. He needs to stop, deliver presents, maybe have some cookies. Let's say he spends 1 millisecond at each home. That's 1,000th of a second. That seems impossibly fast, but let's see what it means. If Santa spends 1 millisecond at each home, that's 1.1 million seconds total, just for stopping at homes. That's about 305 hours. That's about 12.7 days. So even spending just 1 millisecond at each home, Santa would need 12.7 days, not 24 hours. This tells us something important. Santa can't spend even 1 millisecond at each home if he wants to finish in one night. He needs to move so fast that the time spent at each home becomes negligible. He needs to be moving at speeds where stopping and starting don't matter, because the travel time dominates everything. So let's assume Santa spends essentially 0 time at each home. He just flies by, dropping presents as he goes. In this case, his speed is determined entirely by the distance he needs to travel and the time he has available. We calculated earlier that if homes are spread out with an average distance of 500 meters between consecutive homes in an optimized route, Santa needs to travel about 550 million kilometers total. If he has 24 hours, that's 23 million kilometers per hour. That's 6,400 kilometers per second. But wait, we can do better than this. If Santa follows an optimized route, visiting homes in the most efficient order, he might be able to reduce the total distance. The problem of finding the shortest route that visits every home is called the traveling salesman problem, and it's one of the most famous problems in computer science. For 1.1 billion homes, finding the truly optimal route is computationally impossible with current technology, but we can estimate. A good route might reduce the total distance by a factor of 2 or 3 compared to a random route. So instead of 550 million kilometers, Santa might need to travel maybe 200 million kilometers. If Santa travels 200 million kilometers in 24 hours, that's about 8.3 million kilometers per hour. That's about 2,300 kilometers per second. That's still about 600-700 times the speed of sound. The speed of sound in air is about 343 meters per second at sea level, or about 1,235 kilometers per hour. Santa would need to travel thousands of times faster than sound. At these speeds, he would create sonic booms constantly. Every second, he would break the sound barrier thousands of times. The noise would be deafening. The shockwaves would be devastating. A sonic boom occurs when an object travels faster than sound. The object compresses the air in front of it, creating a shockwave. This shockwave travels at the speed of sound, creating a loud boom when it reaches the ground. The Concorde, which traveled at about twice the speed of sound, created sonic booms that could be heard for miles. Santa, traveling thousands of times faster than sound, would create sonic booms of unimaginable intensity. The energy in these shockwaves would be enormous. They could shatter windows, damage buildings, and potentially injure people. If Santa traveled through the atmosphere at these speeds, he would leave a trail of destruction behind him. Entire cities would be subjected to continuous sonic booms. The noise would be constant, unending, devastating. This is why Santa almost certainly couldn't travel through the atmosphere at these speeds. The environmental impact would be catastrophic. He'd need to travel above the atmosphere, in space, where there's no air to create sonic booms. But this creates other challenges, as we'll explore. But there's another way to think about this. What if Santa doesn't travel on the surface? What if he travels in space, above the atmosphere? In space, there's no air resistance, there's no sound barrier. He could travel much faster without creating sonic booms. But even in space, there are limits. The fastest human-made object is the Parker Solar Probe, which reached speeds of about 692,000 km per hour, or about 192 km per second, as it fell toward the Sun. Santa would need to travel about 12 times faster than this. But here's where things get really interesting. As you approach the speed of light, strange things happen. Time slows down for you. Distances contract. This is Einstein's theory of relativity. At 2% of the speed of light, these effects are small but measurable. Santa's clock would run slightly slower than clocks on Earth. From his perspective, the journey might take less time. The speed of light is about 300,000 kilometers per second. If Santa travels at 300 kilometers per second, that's about 0.77% of the speed of light. At this speed, time dilation is minimal. Santa's clock would run about 0.003% slower than Earth clocks. This is measurable but small. But what if Santa could travel faster? What if he could travel at 10% of the speed of light? At 30,000 kilometers per second, time dilation becomes more significant. Santa's clock would run about 0.5% slower. The journey would feel shorter to him. At 50% of the speed of light, time dilation becomes dramatic. Santa's clock would run about 13% slower. At 90% of the speed of light, his clock would run about 56% slower. At 99% of the speed of light, his clock would run about 86% slower. These relativistic effects are real. They've been measured in particle accelerators. Muons, unstable particles created in the upper atmosphere, should decay before reaching the ground. But because they travel at near-light speeds, time dilation allows them to survive the journey. This is experimental proof of Einstein's theory of relativity. But there's a problem. The faster Santa travels, the more energy he needs. Energy requirements increase dramatically as you approach the speed of light. At 50% of light speed, you need about 15% more energy than your rest mass energy. At 90%, you need about 129% more. At 99%, you need about 609% more. The relationship between speed and energy is described by Einstein's famous equation. At low speeds, kinetic energy is proportional to velocity squared. But as you approach light speed, the relationship becomes more complex. The energy required to accelerate increases without bound as you approach the speed of light. This is why nothing with mass can ever reach the speed of light. It would require infinite energy. For Santa's sleigh, this means there's an optimal speed. Too slow, and he can't visit all homes in time. too fast, and the energy requirements become prohibitive. The sweet spot is probably somewhere around 1 to 2% of light speed, where time dilation is minimal, but speeds are still incredibly high. So while traveling faster might help with time, it makes the energy problem much worse. We'll explore energy in detail later. For now, let's stick with more reasonable speeds. But here's another thought. What if we divide the work? What if there are multiple Santas? If we have 10 Santas, each needs to travel 1/10 the distance. If each Santa covers 20 million kilometers in 24 hours, that's about 830,000 kilometers per hour. That's about 230 kilometers per second. That's still about 670 times the speed of sound, but it's more manageable than 600-700 times. If we have 100 Santas, each needs to travel 2 million kilometers in 24 hours. That's about 83,000 kilometers per hour. That's about 23 kilometers per second. That's about 67 times the speed of sound. Still incredibly fast, but getting closer to something that might be theoretically possible. If we have 1,000 Santas, each needs to travel 200,000 kilometers in 24 hours. That's about 300 kilometers per hour. That's about 2.3 kilometers per second. That's about 6.7 times the speed of sound. This is still supersonic, but it's in the range of some experimental aircraft. The fastest aircraft ever built is the State Route 71 Blackbird, which could reach speeds of about 500 kilometers per hour, or about Mach 3.3. That's about 0.97 kilometers per second. With 1,000 Santas, each would need to travel about 2.4 times faster than the Senior 71. This is challenging but not completely impossible. So the speed problem depends on how we solve it. With one Santa, the speeds required are approaching the speed of light, which brings with it all sorts of physics problems. With multiple Santas, the speeds become more reasonable, though still extraordinary. But speed is just one problem. Even if Santa could travel fast enough, he still needs to actually fly. A sleigh needs to generate lift, it needs propulsion, it needs to overcome air resistance. So let's explore the physics of flight, and see what would be needed for a sleigh to actually work. Flight is one of humanity's oldest dreams. For thousands of years, we looked at birds and wondered, how do they do it? How can something heavier than air stay aloft? The answer lies in the physics of aerodynamics, in the delicate balance between lift, drag, thrust, and weight. The history of human flight is fascinating. Leonardo da Vinci sketched flying machines in the 15th century. The Montgolfier brothers launched the first hot air balloon in 1783. The Wright brothers achieved powered flight in 1903. Each breakthrough required understanding the fundamental physics of flight. Each required solving the same problem Santa would face: generating lift, overcoming drag, providing thrust, managing weight. To understand whether a sleigh can fly, we need to understand how flight actually works. The fundamental principle is simple. To fly, you need to generate enough upward force to overcome gravity. This upward force is called lift. But generating lift requires moving through air. And moving through air creates resistance, which is called drag. To overcome drag, you need thrust, a forward force. And all of this must work together to overcome weight, the downward pull of gravity. Gravity is constant. On Earth's surface, it pulls everything downward with a force of about 9.8 meters per second squared. This means every second, a falling object accelerates by 9.8 meters per second. To fly, you must generate enough lift to counteract this constant pull. For a typical aircraft, this means generating lift equal to its weight. For Santa's sleigh, loaded with presents, this could mean generating lift for several tons of material. Aircraft generate lift through their wings. As air flows over and under a wing, it creates a pressure difference. The air moving over the curved top surface travels faster than the air moving under the flat bottom surface. According to Bernoulli's principle, faster moving air has lower pressure, so the pressure above the wing is lower than the pressure below the wing. This pressure difference creates lift, an upward force. But a sleigh doesn't have wings. A traditional sleigh is essentially a box on runners, designed to slide over snow, not fly through air. So how could a sleigh generate lift? There are a few possibilities. First, a sleigh could be redesigned with wings. If we add wings to a sleigh, it becomes more like an aeroplane. The wings could generate lift as the sleigh moves forward. But this changes the fundamental nature of a sleigh. It's no longer a sleigh, it's an aeroplane that looks like a sleigh. Second, a sleigh could use thrust to overcome gravity directly. If you have enough upward thrust, you don't need lift. You can simply push yourself upward against gravity. This is how rockets work. Rockets don't need wings. They just need enough thrust to overcome their weight. But generating enough thrust requires enormous amounts of energy, especially for something as heavy as a sleigh loaded with presents. Third, a sleigh could use some form of anti-gravity or levitation, but we don't know if such technology is possible. Anti-gravity remains firmly in the realm of science fiction. We have no evidence that it's possible, and no theoretical framework that would allow it. So let's focus on what we know is possible: wings and thrust. If a sleigh had wings, it could generate lift, but there's a problem. Lift depends on speed. The faster you move through air, the more lift you generate, but you need to be moving fast enough. For a typical aircraft, you need to be moving at least 100 to 200 kilometers per hour to generate enough lift to take off. But Santa needs to travel much faster than this. He needs to travel at thousands of kilometers per hour. At these speeds, lift becomes less of a problem. The problem becomes drag, air resistance. Air resistance increases with the square of speed. If you double your speed, you quadruple the drag. If you travel 10 times faster, you face 100 times more drag. At the speed Santa needs to travel, air resistance becomes enormous. At 200-300 kilometers per second, which is what we calculated earlier, air resistance would be catastrophic. The drag force would be so large that no material could withstand it. The sleigh would be torn apart by the air itself. The friction would generate so much heat that the sleigh would vaporize. This is why Santa probably couldn't travel through the atmosphere at these speeds. He would need to travel above the atmosphere, in space where there's no air resistance. But this creates another problem. In space, there's no air to generate lift, so a sleigh with wings wouldn't work in space. It would need pure thrust, like a rocket. But here's another thought. What if the sleigh doesn't travel through the atmosphere at all? What if it travels in low Earth orbit, just above the atmosphere? At an altitude of about 100 kilometers, the air is so thin that drag is minimal, but you're still close enough to Earth to make deliveries. In low Earth orbit, a sleigh would need to travel at orbital velocity, which is about 7.8 kilometers per second, or about 28,000 kilometers per hour. This is much slower than the 200-300 kilometers per second we calculated earlier, but it's still incredibly fast. And it's fast enough that, with proper planning, Santa could visit many homes. But there's a problem with orbital travel. To visit homes on the ground, Santa would need to descend from orbit, make the delivery, and then ascend back to orbit. This requires enormous amounts of energy. Each descent and ascent would be like launching a rocket. The energy requirements would be astronomical. Orbital mechanics are complex. To stay in orbit, you need to travel at orbital velocity, which is about 7.8 kilometers per second for low Earth orbit. This speed balances gravity's pull with the tendency to fly off in a straight line. To descend from orbit, you need to slow down, which requires energy. To ascend back to orbit, you need to speed up, which requires even more energy. The energy required to escape Earth's gravity is about 63 megajoules per kilogram. For a 10-ton sleigh, that's 630 gigajoules per trip. If Santa needs to make 1.1 billion deliveries, and each requires a descent and ascent, that's 690 exajoules total. That's about as much energy as the entire world uses in a year. But wait, there's a more efficient approach. Instead of descending to each home individually, Santa could stay in orbit and drop presents. The presents would fall to Earth, guided by small rockets or parachutes. This would eliminate the need for descents and ascents. But it would require incredibly precise targeting. A present dropped from orbit would need to land exactly at the right home, which is a formidable challenge. Alternatively, Santa could use a space elevator or orbital tether system. These theoretical structures would connect Earth's surface to space, allowing travel without rockets. But building such a structure would require materials stronger than anything we currently have. It's another example of how Santa's sleigh would need technologies we haven't invented yet. So maybe the sleigh needs a different approach. Maybe it needs some form of advanced propulsion that we haven't invented yet. Maybe it uses antimatter engines, or fusion drives, or some exotic form of propulsion that defies our current understanding of physics. Let's explore some theoretical propulsion methods. Antimatter engines would be incredibly efficient. When matter and antimatter meet, they annihilate completely, converting all mass to energy. This is the most efficient reaction possible, according to Einstein's E equals mc squared. But producing and storing antimatter is incredibly difficult. We've only produced micrograms of antimatter in particle accelerators. Producing enough for a sleigh engine would require particle accelerators larger than cities, running for years. Fusion drives are another possibility. Nuclear fusion powers the sun. If we could harness fusion for propulsion, we'd have access to enormous amounts of energy. But controlled fusion remains a challenge. We've achieved fusion in laboratories, but maintaining it continuously and extracting useful energy is still being developed. A fusion-powered sleigh would need a compact fusion reactor, something we haven't yet built. Or maybe the sleigh doesn't fly at all in the traditional sense. Maybe it uses some form of teleportation or matter transmission. Maybe it can instantaneously move from one location to another without traveling through the space in between. But this too remains in the realm of science fiction. Quantum teleportation exists, but it only works for information, not matter. You can teleport the quantum state of a particle, but not the particle itself. Matter transmission would require disassembling Santa and the sleigh atom by atom, transmitting the information about their structure, and reassembling them at the destination. This raises profound questions about identity and continuity. Is the reassembled Santa the same Santa, or is it a perfect copy, and the energy requirements would be astronomical? The physics of flight tells us that a traditional sleigh, as we imagine it, cannot fly at the speeds required. It would need wings or thrust, or some form of advanced technology we haven't discovered yet. And even with wings or thrust, traveling through the atmosphere at these speeds would be impossible. The air resistance would destroy anything. So Santa's sleigh would need to travel in space, above the atmosphere, using pure thrust for propulsion. It would need engines powerful enough to overcome gravity and accelerate to incredible speeds. And it would need materials strong enough to survive the journey. But there's another problem we haven't considered yet: the reindeer. According to legend, reindeer pull the sleigh, but can reindeer actually provide the power needed? Let's explore that question next. According to the legend, Santa's sleigh is pulled by reindeer. 8 reindeer, to be precise, with names like Dasher and Dancer. Prancer and Vixen, Comet and Cupid, Donner and Blitzen. And of course, there's Rudolph, with his red nose. But can reindeer actually pull a sleigh through the sky? Can they provide enough power? Let's explore the biology and physics of reindeer. First, let's understand what reindeer actually are. Reindeer, also known as caribou in North America, are large deer native to Arctic and subarctic regions. They're well adapted to cold climates, with thick fur, wide hooves for walking on snow, and the ability to see in near darkness. But they're not magical creatures. They're real animals, bound by the same laws of physics and biology as all living things. Reindeer have been domesticated for thousands of years. Indigenous peoples in northern regions have relied on them for transportation, food, and materials. They're incredibly well suited to their environment. Their hooves change with the seasons, becoming softer in summer for better traction on wet ground, and harder in winter for walking on ice. Their fur has hollow hairs that trap air, providing excellent insulation. They can see ultraviolet light, which helps them navigate in the perpetual twilight of Arctic winters. An adult reindeer typically weighs between 80 and 180 kilograms, or about 175 to 400 pounds. They stand about 1.2 to 1.5 meters tall at the shoulder. They're strong animals, capable of pulling heavy loads. In traditional use, reindeer can pull sleds weighing several hundred kilograms across snow. But there's a crucial difference between pulling a sled on snow and flying through the air. On snow, friction is relatively low. The sled slides easily. The reindeer only needs to overcome this friction, plus the weight of the sled on any uphill sections. In the air, there's no ground to push against. The reindeer would need to generate thrust by moving air, which is much less efficient. But pulling a sled across snow is very different from flying through the air. On the ground, reindeer push against the ground with their hooves. The ground pushes back, providing the force needed to move forward. This is Newton's third law. For every action, there's an equal and opposite reaction. In the air, there's no ground to push against. To fly, reindeer would need to push against the air itself. But air is much less dense than ground. Pushing against air requires moving air backward, which creates thrust. But generating enough thrust to overcome gravity and fly requires moving a lot of air very fast. Birds fly by flapping their wings. As a bird flaps its wings downward, it pushes air downward. According to Newton's third law, the air pushes the bird upward. This creates lift. But birds are specifically adapted for flight. Their wings are large relative to their body size. Their muscles are powerful, their bones are hollow to reduce weight. Reindeer don't have wings. They have legs. Their legs are adapted for running and walking, not flying. Even if reindeer could somehow generate thrust, they would need enormous power to overcome their weight and the weight of the sleigh. Let's do some calculations. A typical reindeer might be able to generate about 1 horsepower of sustained power, or about 750 watts. This is impressive for an animal, but it's not nearly enough for flight. A small aircraft engine generates thousands of horsepower. A commercial jet engine generates tens of thousands of horsepower. But let's be generous. Let's say a reindeer could generate 10 horsepower, or about 7,500 watts. That's 10 times what a typical reindeer can do, but let's see what it means. To fly, you need to overcome gravity. Gravity pulls downward, with a force equal to weight. For a reindeer weighing 150 kilograms, gravity pulls with a force of about 1,470 newtons. To overcome this and fly upward, you need to generate at least 1,470 newtons of upward force. But generating upward force requires moving air downward. The amount of force you can generate depends on how much air you move and how fast you move it. To generate 470 newtons of force, a reindeer would need to move about 150 kilograms of air downward every second, at a speed of about 10 meters per second. That's a lot of air. But reindeer don't have wings, they can't move air efficiently. Even if they could, generating 470 newtons of force would require enormous power. The power needed is force times velocity. If you're moving air at 10 meters per second to generate 470 newtons of force, you need at least 700 watts of power, or about 20 horsepower. So even to lift just the reindeer itself, you'd need about 20 horsepower per reindeer. But Santa's sleigh is much heavier than a reindeer. A sleigh loaded with presents might weigh several tons. To lift that, you'd need hundreds or thousands of horsepower. 8 reindeer, each generating 20 horsepower, would provide 160 horsepower total. That's enough to lift about 200 kilograms, or about 600 pounds. But Santa's sleigh, loaded with presents for billions of children, would weigh much more than that. But wait. We're thinking about this wrong. Reindeer don't need to lift the sleigh, they need to pull it forward. In traditional use, reindeer pull sleds across the ground. The sled slides on snow, which has low friction. So reindeer don't need to overcome the full weight of the sled, they just need to overcome friction. But in the air, it's different. To move forward through the air, you need to overcome air resistance, drag. At the speed Santa needs to travel, drag is enormous. To overcome drag, you need thrust. And generating thrust requires power. At 300 kilometers per second, the drag on a sleigh would be astronomical. To overcome this drag, you'd need engines generating millions of horsepower. 8 reindeer, even super-powered reindeer, couldn't provide this. So reindeer as we know them cannot power Santa's sleigh. They're simply not capable of generating enough power. Even if we imagine reindeer that are 10 times stronger, or 100 times stronger, they still couldn't provide the power needed. But what if reindeer were different? What if they were genetically engineered? What if they were cybernetically enhanced? What if they were magical creatures with capabilities beyond normal biology? These are interesting questions, but they take us into the realm of speculation. The biology of reindeer, as we understand it, has limits. Those limits are determined by physics, by the efficiency of muscles, by the energy available from food. Muscle efficiency is limited. Even the most efficient muscles convert only about 25% of chemical energy into mechanical work. The rest is lost as heat. So even if reindeer could somehow access unlimited energy, they would still be limited by muscle efficiency. To understand muscle efficiency, think about how muscles work. When you contract a muscle, chemical energy stored in molecules like ATP is converted to mechanical work. But this conversion isn't perfect. Some energy is always lost as heat. The most efficient muscles in nature, like those in hummingbirds, convert about 25% of chemical energy to mechanical work. Human muscles are less efficient, converting about 20%, so even perfect muscles have limits. And energy itself is limited. Reindeer get energy from food. Food provides chemical energy that muscles can use. But there's a limit to how much energy a reindeer can process. Even if a reindeer ate constantly, it couldn't process enough energy to power flight at the speeds required. A reindeer's metabolism is impressive. They can process large amounts of food, especially in preparation for winter. But there's a physical limit to how fast they can digest and metabolize food. Even if we imagine a reindeer with a supercharged metabolism, processing food 10 times faster than normal, it still wouldn't be enough. The energy requirements for flight at these speeds are simply too enormous. What if reindeer were enhanced with technology? What if they had mechanical wings attached? What if they had jet engines? At that point, they're not really reindeer anymore, they're more like biological components in a mechanical system. The reindeer would become essentially decorative, serving no functional purpose beyond perhaps navigation or symbolism. So the reindeer problem, like the flight problem, points to the need for advanced technology. Reindeer, as we know them, cannot provide the power needed. Santa's sleigh would need engines, or some form of propulsion that goes far beyond biological capabilities. But this doesn't mean reindeer are useless. Perhaps they serve a different purpose. Perhaps they're navigators, using their ability to see in darkness to guide the sleigh. Perhaps they're symbols, representing the magic of the journey, rather than its power source. Or perhaps, in a world where Santa's sleigh actually works, reindeer have been enhanced in ways we can't yet imagine. Perhaps they've been given wings, or cybernetic enhancements, or magical abilities that transcend normal biology. But for now, the biology and physics tell us that reindeer, as we know them, cannot power Santa's sleigh. The sleigh would need engines, or some form of advanced propulsion, and those engines would need enormous amounts of energy. So let's explore the energy problem next. Energy is the fundamental requirement for any journey. To move, you need energy. To move fast, you need a lot of energy. To move incredibly fast, you need an almost unimaginable amount of energy. So how much energy would Santa's sleigh actually need? Energy is one of the most fundamental concepts in physics. It can't be created or destroyed, only converted from one form to another. When you burn gasoline in a car engine, chemical energy converts to kinetic energy. When you charge a battery, electrical energy converts to chemical energy. When you lift something, you're converting kinetic energy to potential energy. Let's start with the basics. Energy comes in many forms: chemical energy stored in fuel, electrical energy stored in batteries, nuclear energy from atoms, kinetic energy from motion, potential energy from position. For Santa's sleigh, we need energy to accelerate, to overcome air resistance, to carry presents, and to navigate. The unit we use to measure energy is the joule. 1 joule is the energy needed to lift a small apple 1 meter against Earth's gravity. It's a tiny amount of energy. But when you start talking about moving massive objects at incredible speeds, the numbers become astronomical. A typical human uses about 2,000 kilojoules of energy per day from food. That's 2 million joules. Santa's sleigh would need trillions of times more energy than that. The most fundamental energy requirement is kinetic energy. Kinetic energy is the energy of motion. The faster something moves, the more kinetic energy it has. The formula is simple. Kinetic energy equals 1/2 times mass times velocity squared. The velocity is squared, which means energy increases dramatically as speed increases. If Santa's sleigh, loaded with presents, weighs about 10,000 kilograms or 10 metric tons, and if it travels at 200-300 kilometers per second, then its kinetic energy would be enormous. Let's calculate 1/2 times 10,000 kilograms times 300,000 meters per second squared. That's about 2.6 times 10 to the 16th power joules. A joule is a unit of energy. To put this in perspective, a typical car uses about 100 megajoules, or 100 million joules, of energy to travel 100 kilometers. Santa's sleigh would have kinetic energy equivalent to about 260 billion car trips. That's an enormous amount of energy. But kinetic energy is just the energy of motion. Santa also needs energy to accelerate. To go from rest to 300 kilometers per second, the sleigh needs to gain kinetic energy. This requires work, which is force times distance. The faster you want to accelerate, the more force you need, and the more energy you need. If Santa accelerates from rest to 300 km per second in, say, 1 hour, his acceleration would be about 640 meters per second squared. That's about 65 times the acceleration due to gravity. This is enormous acceleration. The force needed would be mass times acceleration, or about 6.4 million newtons. The energy needed would be force times distance, which depends on how far he travels during acceleration. But acceleration is just the beginning. Once Santa is moving, he needs energy to overcome air resistance, drag. At high speeds, drag becomes the dominant force. Drag increases with the square of speed, so at 300 km per second, drag would be astronomical. In the atmosphere, drag would destroy the sleigh. So Santa would need to travel in space, above the atmosphere. But even in space there are challenges. To stay in orbit you need orbital velocity. To change orbits you need energy. To descend to Earth's surface and ascend back to space, you need enormous amounts of energy. Each descent and ascent would be like launching a rocket. The energy required to escape Earth's gravity is about 63 megajoules per kilogram. For a 10-ton sleigh, that's about 630 gigajoules per trip. If Santa needs to make 1.1 billion deliveries, and each requires a descent and ascent, that's about 690 exajoules total. An exajoule is 10 to the 18th power joules, or a billion joules. To put this in perspective, global energy consumption in 2024 was about 670 exajoules per year. So Santa would need about as much energy as the entire world uses in a year, just for the descents and ascents. But wait. We calculated earlier that with multiple Santas, the energy requirements per Santa would be much lower. If we have 1,000 Santas, each making 1.1 million deliveries, each would need about 690 petajoules. A petajoule is 10 to the 15th power joules, or 1,000 billion joules. That's still enormous, but more manageable. But where would this energy come from? What energy sources could provide this much power? Chemical fuels like gasoline or rocket fuel have limited energy density. Gasoline contains about 46 megajoules per kilogram. To provide 690 petajoules, you'd need about 15 billion kilograms of gasoline. That's 15 million metric tons. That's about 150,000 fully loaded cargo ships. This is clearly impractical. Batteries have even lower energy density. The best lithium-ion batteries store about 0.9 megajoules per kilogram. To provide 690 petajoules, you'd need about 770 billion kilograms of batteries. That's 770 million metric tons. This is completely impractical. Nuclear energy is more promising. Nuclear fission, splitting atoms, releases about 80 terajoules per kilogram of fuel. To provide 690 petajoules, you'd need about 600 kilograms of nuclear fuel. That's about 8.6 metric tons. This is still heavy, but more reasonable. Nuclear fusion, combining atoms, releases even more energy. Fusion of hydrogen releases about 600 terajoules per kilogram. To provide 690 petajoules, you'd need about 150 kilograms of hydrogen fuel. That's just over 1 metric ton. This is much more reasonable. But there's a problem. Nuclear reactors, whether fission or fusion, are heavy. They require shielding, cooling, and control systems. A practical nuclear-powered sleigh would weigh much more than just the fuel. It might weigh hundreds of tons. And there's another problem. Even with nuclear power, generating enough power continuously is challenging. A typical nuclear reactor generates about 1 gigawatt of power. To provide 690 petajoules in 24 hours, you'd need about 8 terawatts of power. That's 8,000 times more than a typical reactor. So Santa would need thousands of nuclear reactors, or one enormous reactor. Either way, the sleigh would be massive, which makes acceleration even harder, which requires even more energy. It's a vicious cycle. But what about antimatter? Antimatter, when it meets matter, annihilates completely, converting all mass to energy. According to Einstein's famous equation, E equals mc squared, 1 kilogram of antimatter annihilating with 1 kilogram of matter would release about 90 petajoules of energy. So just 7.7 kilograms of antimatter would provide 690 petajoules. This sounds promising, but antimatter is incredibly difficult to produce and store. We've only produced tiny amounts, micrograms at most. Producing kilograms would require enormous particle accelerators running for years. And storing antimatter requires magnetic fields and vacuum chambers, which add weight and complexity. Antimatter was first predicted by Paul Dirac in 1928. The first antimatter particle, the positron, was discovered in 1932. Since then, we've learned to produce small amounts of antimatter in particle accelerators. But production is incredibly inefficient. It takes far more energy to produce antimatter than the antimatter itself contains. We're nowhere near the break-even point where antimatter production becomes practical. Storing antimatter is another challenge. Antimatter annihilates instantly when it touches normal matter, so it must be stored in magnetic fields, suspended in a vacuum. The storage systems are massive and energy-intensive. For Santa's sleigh, the storage system might weigh more than the antimatter itself, negating the advantage of its high energy density. What about other exotic energy sources? Dark energy, zero-point energy, these remain purely theoretical. We don't know if they can be harnessed, or even if they exist in a form we could use. They're fascinating possibilities, but they don't help us solve the practical problem. So the energy problem is profound. Santa's sleigh would need energy sources that don't yet exist, or energy sources that are impractical with current technology. The energy requirements are so large that they approach the limits of what's physically possible. But energy is just one challenge. Even if we had unlimited energy, we'd still need materials that could survive the journey. So let's explore materials science next. Even if Santa's sleigh had unlimited energy and could travel at incredible speeds, it would still need to survive the journey. The materials it's made from would face extreme conditions: heat, pressure, acceleration and stress. So what materials would be needed? What could survive? Let's start with heat. When you move through air at high speeds, friction generates heat. The faster you move, the more heat you generate. At supersonic speeds, aircraft surfaces can reach hundreds of degrees Celsius. At hypersonic speeds, thousands of degrees. At the speed Santa needs to travel, even in the thin upper atmosphere, temperatures would be extreme. The space shuttle, re-entering Earth's atmosphere at about 7.8 kilometers per second, experienced temperatures up to 1,650 degrees Celsius on its nose and leading edges. Santa, traveling at 200-300 kilometers per second, would experience much higher temperatures, even in space where there's no air resistance. But wait. In space there's no air, so there's no friction, so there's no heat from friction. But there are other sources of heat. Solar radiation, cosmic radiation. And if Santa travels through the upper atmosphere, even briefly, friction would generate enormous heat. So the sleigh would need materials that can withstand extreme temperatures. Most metals melt at temperatures below 2000 degrees Celsius. Steel melts at about 1,500 degrees. Aluminum melts at about 660 degrees. Even titanium, which has a high melting point, melts at about 1670 degrees. Some materials can withstand higher temperatures. Tungsten melts at about 300–400 degrees Celsius. Carbon, in the form of graphite, can withstand temperatures up to about 300–600 degrees before sublimating. But these materials have other problems. Tungsten is very heavy. Graphite is brittle. Ceramic materials can withstand even higher temperatures. Some ceramics can survive temperatures above 2000 degrees Celsius. But ceramics are brittle. They crack under stress. They're not good for structural applications. Scientists are developing new materials that combine the heat resistance of ceramics with the toughness of metals. These ceramic matrix composites could potentially withstand higher temperatures while remaining structurally sound. But even these advanced materials would struggle at the temperatures Santa's sleigh would encounter. The heat problem is compounded by the fact that different parts of the sleigh would experience different temperatures. The leading edges, where air resistance is greatest, would be hottest. The trailing edges would be cooler. This temperature gradient would create thermal stresses, causing materials to expand and contract at different rates. This could cause cracking, warping, or even structural failure. But heat isn't the only challenge. There's also acceleration. When Santa accelerates or decelerates, everything in the sleigh experiences forces. These forces are measured in G's, multiples of Earth's gravity. 1 G is the acceleration due to gravity, about 9.8 meters per second squared. Acceleration creates inertial forces. When you accelerate forward, everything inside the vehicle feels pushed backward. When you brake, everything feels pushed forward. These forces are proportional to the acceleration. The faster you accelerate, the stronger the forces become. If Santa accelerates at 65 Gs, as we calculated earlier, everything in the sleigh experiences 65 times its normal weight. A 1 kilogram present would feel like it weighs 65 kilograms. A person would be crushed. Most materials would fail under such stress. The human body can withstand about 9 Gs for short periods, with proper training and equipment. Fighter pilots can withstand about 9 Gs with G-suits that prevent blood from pooling. But 65 Gs would be fatal, so the sleigh itself would need to be incredibly strong. It would need to withstand forces 65 times its weight. This requires materials with high strength-to-weight ratios. The stronger a material is relative to its weight, the better it is for this application. Steel has a strength-to-weight ratio of about 0.2. This means steel can support about 0.2 times its weight before failing. To support 65 times its weight, steel would need to be 325 times stronger, or the structure would need to be 325 times larger, which adds weight, which makes the problem worse. Carbon fiber has a much better strength-to-weight ratio, about 1.5. This is much better than steel, but even carbon fiber would struggle under 65 Gs. The structure would need to be carefully designed, with reinforcements and supports. Graphene, a single layer of carbon atoms, has an even better strength-to-weight ratio, potentially up to 100 or more. But graphene is difficult to manufacture in large quantities, and even graphene has limits. But there's another problem. Materials don't just need to be strong. They need to be strong under extreme conditions. At high temperatures, materials weaken. At high speeds, vibrations and oscillations can cause fatigue failure. Materials need to maintain their properties under all conditions. And there's the weight problem. Every kilogram of material adds to the total weight. More weight means more energy needed to accelerate. More energy means more fuel. More fuel means more weight. It's another vicious cycle. So the sleigh would need to be made from the lightest, strongest materials possible. It would need advanced composites, perhaps carbon fiber reinforced with graphene. It would need careful engineering to minimize weight while maximizing strength. But even with the best materials, the sleigh would be heavy. A 10-ton sleigh is already heavy. With all the engines, fuel and structure needed, it might weigh hundreds of tons. This makes acceleration even harder, which requires even more energy, which requires even more fuel, which adds even more weight. So materials, science tells us that building a sleigh that can survive the journey would require materials and engineering that don't yet exist. We'd need materials stronger than anything we currently have, lighter than anything we currently have, and capable of withstanding conditions more extreme than anything we've ever encountered. Scientists are constantly working on new materials. Carbon nanotubes discovered in 1991 are incredibly strong and light. They're being explored for use in everything from electronics to space elevators. Metamaterials, engineered materials with properties not found in nature, could potentially help with heat management or structural integrity. But even these cutting-edge materials fall short of what Santa's sleigh would need. The materials problem highlights a fundamental challenge. We're asking materials to do things they've never been asked to do before. We're asking them to withstand forces that would destroy anything we've ever built. We're asking them to maintain their properties under conditions more extreme than anything we've ever encountered. This isn't just difficult. It might be fundamentally impossible with materials as we understand them. But materials are just one part of the challenge. There's also the problem of navigation and logistics. How would Santa find every home? How would he navigate efficiently? So let's explore the logistics problem next. One of the clever aspects of Santa's legend is how he uses Earth's rotation to his advantage. By following the night around the planet, he extends his available time. But how does this actually work? And how much does it help? Let's start with the basics. Earth rotates on its axis once every 24 hours. As it rotates, different parts of the planet face the sun, creating day and night. But Earth is divided into time zones, regions that share the same standard time. There are 24 time zones, one for each hour of the day. When it's midnight in one time zone, it's 11 p.m. in the time zone to the west, and 1 a.m. in the time zone to the east. So as Santa travels westward, following the night, he can extend his available time. But here's the key insight. Santa doesn't need to visit homes only at midnight. He can visit them any time during the night. In most places, night lasts about 12 hours. So Santa has about 12 hours of darkness in each location to make deliveries. But Santa is moving. As he travels westward, he's staying in the night, so he's not limited to 12 hours total. He's limited to 12 hours per location, but he can visit many locations, one after another, as he follows the night. Let's think about this more carefully. Santa starts at the international dateline, where Christmas Eve begins. This is in the Pacific Ocean, roughly between New Zealand and Hawaii. As Earth rotates, night falls in this region first. Santa then travels westward, staying ahead of the sunrise. As he travels, he visits homes in each time zone. By the time he reaches the last time zone, where Christmas Eve ends, he's been traveling for about 24 hours, following the night around the planet. But here's the problem. Santa can't be everywhere at once. He can only visit one home at a time. So even though he has 24 hours total, he still needs to visit 1.1 billion homes. The time zone trick doesn't reduce the number of homes. It just extends the total time available. But it does help in another way. By following the night, Santa ensures that he's always visiting homes when it's dark. when children are sleeping. This makes sense from a story perspective. But from a physics perspective, it doesn't solve the fundamental problem of speed. However, there's another way to think about time zones. What if Santa doesn't travel alone? What if there are multiple Santas, each covering different time zones? If we have 24 Santas, one for each time zone, each Santa would only need to visit homes in their assigned time zone. The number of homes per time zone varies. Some time zones, like those covering China or India, have hundreds of millions of people. Other time zones, like those in the Pacific, have very few people. So some Santas would be much busier than others. But if we divide homes evenly among 24 Santas, each would need to visit about 46 million homes. If each Santa has 12 hours of night in their time zone, that's 43,200 seconds. So each Santa would need to visit about 1,065 homes per second. That's still incredibly fast, but it's about 12 times slower than if one Santa visited all homes. And here's another advantage. Each Santa only needs to travel within their time zone. The distance within a time zone varies, but it's much less than traveling around the entire planet. So each Santa's travel distance would be much shorter. For example, if a time zone spans about 1,670 kilometers at the equator, and if homes in that time zone are spread over, say, 5,000 kilometers north to south, then a Santa covering that time zone might need to travel about 10 million kilometers total, visiting 46 million homes. That's about 230 kilometers per home, on average. If that Santa has 12 hours, or 43,200 seconds, to visit 46 million homes, they'd need to travel at about 230,000 kilometers per hour, or about 64 kilometers per second. That's still incredibly fast, about 186 times the speed of sound, but it's much more manageable than 200-300 kilometers per second. So the time zone solution, combined with multiple Santas, makes the problem more tractable. It doesn't solve everything, but it reduces the requirements significantly. Instead of one Santa traveling at near light speeds, we could have 24 Santas traveling at supersonic speeds. This is still challenging, but it's closer to what might be theoretically possible. But there's another consideration. Time zones aren't just about time. They're also about geography. Some time zones cover vast areas with few people, others cover small areas with many people. So dividing by time zones might not be the most efficient approach. A better approach might be to divide by population density. Have more Santas in densely populated areas, fewer in sparsely populated areas. Or divide by continents. Have Santas responsible for entire continents, regardless of time zones. But regardless of how we divide the work, the time zone solution helps. It extends the available time. It allows Santa or Santas to work through multiple nights, following the darkness around the planet. It's a clever use of Earth's rotation, and it makes the challenge slightly more manageable. But time zones are just one part of the logistics problem. There's also the challenge of finding every home, navigating efficiently, and delivering the right presents. So let's explore the full logistics nightmare next. Even if Santa could travel fast enough, generate enough power, and build a sleigh strong enough to survive, he'd still face an enormous logistics challenge. How does he find every home? How does he navigate efficiently? How does he deliver the right presents to the right children? Let's start with finding homes. There are about 1.1 billion homes with children in the world. Santa needs to visit each one. But how does he know where they are? How does he find them? In the modern world, we have GPS, satellite imagery, and detailed maps. Santa could use these technologies to locate every home, but there are challenges. Not every home is in a database. Some homes are in remote locations. Some are in areas without clear addresses. Some are temporary structures. But let's assume Santa has perfect knowledge of every home's location. He has GPS coordinates for all 1.1 billion homes. Now he needs to plan a route. He needs to visit every home exactly once, in the most efficient order possible. This is the traveling salesman problem, one of the most famous problems in computer science. Given a list of cities, or in this case homes, and the distances between them, find the shortest route that visits each city exactly once and returns to the starting point. The traveling salesman problem was first formulated in the 1930s. It seems simple at first glance. But as the number of locations increases, the problem becomes exponentially more complex. For just 5 cities, there are 120 possible routes. For 10 cities, there are 3.6 million possible routes. For 20 cities, there are about 2.4 quintillion possible routes. The number of routes grows as the factorial of the number of cities. For small numbers of cities, this problem is solvable. For 10 cities, there are about 3.6 million possible routes. A computer can check them all. For 20 cities, there are about 2.4 quintillion possible routes. This is getting difficult, but still possible with enough computing power. But for 1.1 billion homes, the number of possible routes is astronomical. It's larger than the number of atoms in the observable universe. Finding the truly optimal route is computationally impossible, even with the most powerful computers imaginable. To understand the scale, imagine if every atom in the observable universe was a supercomputer, and each supercomputer could check one route per second. Even with this unimaginable computing power, it would take longer than the age of the universe to check all possible routes. The problem is fundamentally intractable for this scale. But we don't need the optimal route, we just need a good route. There are algorithms that can find routes that are within a few percent of optimal. These algorithms use heuristics, rules of thumb, to find good solutions without checking every possibility. The nearest neighbor algorithm is one simple approach. Start at a random home, then always visit the nearest unvisited home. This is fast but not very good, typically finding routes that are 25% longer than optimal. More sophisticated algorithms use techniques like simulated annealing, genetic algorithms, or ant colony optimization. These can find routes within 5 to 10% of optimal. One approach is to divide the problem, divide Earth into regions, find good routes within each region, then connect the regions. This doesn't give the optimal solution, but it gives a solution that's good enough. For Santa's route, we could divide Earth into continents, then into countries, then into cities. Within each city we could find an optimal route. Then we'd connect the cities, the countries, and the continents. This hierarchical approach reduces the computational complexity dramatically, though it sacrifices some optimality. Another approach is to use clustering. Group nearby homes together, visit all homes in a cluster before moving to the next cluster. This reduces the total distance traveled. Clustering algorithms can identify natural groupings of homes. In a city, homes naturally cluster in neighborhoods. In rural areas, homes cluster around towns. By visiting all homes in a cluster before moving to the next, Santa minimizes the number of long-distance jumps between clusters. But even with good algorithms, planning a route for 1.1 billion homes would require enormous computing power. It would take years of computation, even with the fastest supercomputers, so Santa would need to start planning months or years in advance. The world's fastest supercomputer can perform about 500 quadrillion calculations per second. Even with this power, finding a good route for 1.1 billion homes would take months. Santa would need to start planning in January for the following December. And the route would need constant updates as homes are built, demolished, or children move. But let's assume Santa has a route planned. Now he needs to navigate. He needs to follow the route precisely, visiting each home in order. This requires precise navigation, precise timing, and precise control. GPS provides location accuracy of about 3 to 5 meters. This is good enough for most purposes, but at the speed Santa needs to travel, even small errors could cause him to miss homes. If he's traveling at 200-300 kilometers per second, and if his navigation is off by even 1 meter, he could miss a home entirely. At 200-300 kilometers per second, Santa travels about 2.3 meters in 1 microsecond. So if his navigation is off by even a few meters, he could pass right by a home without noticing. The precision required is extraordinary. He'd need navigation accurate to within centimeters, updated thousands of times per second. So Santa would need more precise navigation. He might need inertial navigation systems, which use accelerometers and gyroscopes to track position. Or he might need ground-based navigation beacons. Or he might need some form of quantum navigation that we haven't invented yet. Inertial navigation systems work by measuring acceleration and rotation. By integrating these measurements over time, they can track position without external references. But they accumulate errors over time. Even the most precise inertial systems drift by meters per hour. For Santa's journey, this would be unacceptable. Ground-based navigation beacons could provide more precision. If every home had a navigation beacon, Santa could home in on each one precisely. But installing beacons at 1.1 billion homes would be an enormous infrastructure project, and maintaining them would be a constant challenge. Quantum navigation is a theoretical possibility. Quantum sensors can measure gravitational fields with incredible precision. By mapping Earth's gravitational field in detail, Santa could navigate using gravity alone. But this technology is still in early development, and the precision required would be beyond anything we've achieved. But navigation is just one challenge. There's also entry. How does Santa get into each home? According to legend, he comes down the chimney. But not every home has a chimney. Many modern homes don't have fireplaces at all. So Santa would need alternative entry methods. He might use doors, windows, or other openings. Or he might use some form of matter transmission, passing through walls. But this takes us into science fiction territory. And there's the present problem. Santa needs to carry presents for billions of children. How many presents is that? If each child gets, on average, 3 presents, that's about 6.6 billion presents total. How does Santa carry all of these? A typical present might weigh about 0.5 kilograms. So 6.6 billion presents would weigh about 3.3 billion kilograms, or 3.3 million metric tons. This is clearly impossible to carry. To put this in perspective, the largest cargo ship in the world can carry about 200,000 metric tons. Santa would need about 16,500 of these ships just to carry the presents. That's more cargo ships than exist in the entire world. And that's assuming the presents are perfectly packed, with no wasted space. But wait, there's more. Presents come in all shapes and sizes. Some are small, like jewelry or books. Some are large, like bicycles or furniture. The volume problem is even worse than the weight problem. A typical present might occupy about 0.01 cubic meters. So 6.6 billion presents would occupy about 66 million cubic meters. That's a cube about 400 meters on each side. That's taller than the Empire State Building. So Santa would need some form of matter compression or storage. Perhaps presents are stored in a compressed form and expanded at delivery. Perhaps they're stored in a higher dimensional space. Perhaps they're replicated on demand using advanced manufacturing. The compression idea is interesting. If we could compress matter to the density of a neutron star, where atoms are crushed together, we could reduce the volume dramatically. But neutron star matter is incredibly dense. A teaspoon would weigh billions of tons. And creating or storing matter at that density would require technology far beyond anything we can imagine. But even with compression or replication, Santa would need to know what each child wants. He'd need a list, a database of wishes and requests. He'd need to know which children have been naughty and which have been nice. He'd need to match presents to children. This is another enormous data problem. Maintaining a database of 2.2 billion children, tracking their behavior, managing their wish lists, coordinating deliveries. This would require computing infrastructure beyond anything that currently exists. Let's think about the data requirements. For each child, Santa would need to store name, address, age, wish list, behavior record, and delivery status. That's probably about 1 kilobyte per child. For 2.2 billion children, that's about 2.2 terabytes of data. That's manageable with modern storage technology. But the real challenge is processing this data in real time, updating it constantly, and using it to coordinate deliveries. The naughty/nice determination is particularly complex. How do you measure behavior? Is it based on school performance, helpfulness at home, kindness to others? And how do you collect this information? Does Santa have surveillance systems monitoring every child? Does he have informants? The logistics of behavior tracking alone would be mind-boggling. Then there's the wish list problem. Children's wishes change constantly. A child might want a toy in October, but change their mind by December. How does Santa keep track? Does he monitor social media? Does he intercept letters? Does he use predictive algorithms to guess what children want? The data collection and processing requirements would be enormous. But here's where the multiple Santas solution really helps. If we divide the work among many Santas, each Santa only needs to handle a fraction of the homes and children. If we have 1,000 Santas, each handles about 1.1 million homes and 2.2 million children. This is still enormous, but more manageable. And with multiple Santas, we can have regional workshops. Instead of one North Pole, we could have workshops in different regions. Each workshop could produce presents for its region. Each Santa could start from their regional workshop, reducing travel distance. We could divide Earth into continents. One Santa for North America. One for South America. One for Europe. One for Africa. Two for Asia, given its large population. One for Australia and Oceania. That's 7 Santas total. Or, we could divide by population density. More Santas in densely populated areas, like China, India, and Europe. Fewer in sparsely populated areas like Australia or the Arctic. This would balance the workload more evenly. Or we could have 1 Santa per time zone, as we discussed earlier. That's 24 Santas, each covering their assigned time zone. This ensures that each Santa works during their local night, which makes sense from a story perspective. But regardless of how we divide the work, coordination becomes crucial. Multiple Santas need to communicate. They need to ensure no gaps or overlaps. They need to share information about routes, deliveries, and problems. Imagine the coordination challenge. With 24 Santas working simultaneously, each needs to know their territory precisely. There can't be any gaps where homes are missed. There can't be any overlaps where homes are visited twice. The boundaries between territories need to be perfectly defined. And if one Santa encounters a problem, The others need to know immediately, so they can adjust their routes. This would require a Santa network, a communication system connecting all Santas. They might use quantum entanglement for instant communication. Quantum entanglement is a real phenomenon where two particles become linked, so that measuring one instantly affects the other, regardless of distance. This could theoretically allow instant communication across vast distances, but we haven't yet figured out how to use quantum entanglement for practical communication. Or they might use advanced radio systems, but radio waves travel at the speed of light, which means there would be delays. For Santas working on opposite sides of the planet, the delay would be about 0.07 seconds. That's small, but at the speeds they're traveling, even small delays could cause problems. Or they might use some form of technology we haven't invented yet. Perhaps faster-than-light communication, though this would violate our current understanding of physics. Perhaps some form of subspace communication, borrowing concepts from science fiction. The coordination challenge is almost as complex as the delivery challenge itself. The logistics challenge is enormous. Finding homes, planning routes, navigating precisely, entering homes, delivering presents, coordinating multiple Santas. Each aspect is challenging on its own. Together they create a problem of almost unimaginable complexity. But logistics problems have solutions. They might require advanced technology, they might require multiple agents working together, they might require computing power beyond our current capabilities. But they're not fundamentally impossible, they're just enormously difficult. So the logistics challenge, like the speed challenge and the energy challenge, points to the need for advanced technology. But it also suggests that with enough Santas, enough computing power, and enough coordination, the problem might be solvable. Not easy, but solvable. And this brings us to the question of solutions. What technologies would actually make Santa's sleigh work? What would be needed? So let's explore practical and theoretical solutions next. We've explored the challenges: speed, flight, reindeer, energy, materials, time zones, logistics. Each challenge is enormous on its own. Together, they seem insurmountable. But what if we combine solutions? What if we use multiple Santas? What if we use advanced technology? What would actually be needed? Let's start with the most practical solution: multiple Santas. This isn't just a way to reduce the workload. It's a fundamental rethinking of the problem. Instead of one impossible journey, we have many difficult but potentially achievable journeys. Let's think about how to divide the work. We could divide by continents. North America has about 370 million children. South America has about 150 million. Europe has about 100 million. Africa has about 600 million. Asia has about 900 million. Australia and Oceania have about 10 million. That's about 2.1 billion total, close to our 2.2 billion estimate. If we assign Santas based on population, we might have one Santa for North America, one for South America, one for Europe, two for Africa, three for Asia, and one for Australia. That's 9 Santas total. But continents are large and diverse. A better approach might be to divide by regions within continents. For example, Asia could be divided into East Asia, South Asia, and Southeast Asia. Each region would have its own Santa. Or we could divide by time zones, as we discussed earlier, 24 Santas, one for each time zone. This ensures that each Santa works during their local night, which makes sense from both a story and practical perspective. But let's think about what each Santa would need. If we have 24 Santas, each covering one time zone, each would need to visit about 46 million homes. Each would need to travel about 10 million kilometers in 12 hours. That's about 230,000 kilometers per hour. or about 64 kilometers per second. This is still incredibly fast, about 186 times the speed of sound, but it's much more manageable than 200-300 kilometers per second. It's in the range of what might be theoretically possible with advanced propulsion. Each Santa would need a sleigh with advanced engines. Perhaps fusion engines, using nuclear fusion to generate thrust. Or perhaps antimatter engines, using matter-antimatter annihilation. Or perhaps some form of propulsion we haven't invented yet. Each sleigh would need to be made from advanced materials, carbon fiber composites reinforced with graphene. Materials that can withstand extreme temperatures and forces. Materials that are strong but light. Each Santa would need advanced navigation systems. GPS combined with inertial navigation. Quantum sensors for precise positioning. AI systems for route optimization and real-time adjustments. Each Santa would need a regional workshop. Instead of one North Pole, we'd have workshops in different regions. Each workshop would produce presents for its region. Each Santa would start from their workshop, reducing initial travel distance. The workshops would need advanced manufacturing, 3D printing on demand, matter replication, or perhaps traditional manufacturing at enormous scale. Each workshop would need to produce millions of presents, matching them to children's wishes. The Santas would need to coordinate. They'd need a communication network, perhaps quantum entanglement for instant communication across vast distances. Or perhaps advanced radio systems. They'd need to share information, coordinate routes, ensure no gaps or overlaps. This is still enormously challenging. But it's more realistic than one Santa doing everything. With 24 Santas, each traveling at 64 kilometers per second, using advanced propulsion and materials, the problem becomes difficult, but not fundamentally impossible. But what about more theoretical solutions? What if we could use advanced physics to make the journey easier? One possibility is time dilation. According to Einstein's theory of relativity, time slows down for objects moving at high speeds. If Santa travels at a significant fraction of the speed of light, time would pass more slowly for him. From his perspective, the journey might take less time. But there's a problem. Time dilation helps Santa, but it doesn't help the children waiting for presents. From Earth's perspective, time passes normally. So even if Santa experiences less time, he still needs to visit all the homes from Earth's perspective. Another possibility is wormholes. A wormhole is a theoretical shortcut through space-time. If Santa could create or use a wormhole, he could travel vast distances instantly, without actually moving through the space in between. But wormholes are purely theoretical. We don't know if they exist, we don't know if they can be created, we don't know if they could be used for travel. They remain in the realm of science fiction. Another possibility is teleportation. If Santa could teleport from one location to another, he wouldn't need to travel at all. He could simply appear at each home, deliver presents, and disappear. But teleportation, as we understand it, would require disassembling Santa and the sleigh, transmitting the information about their structure, and reassembling them at the destination. This raises profound questions about identity and continuity. Is the reassembled Santa the same Santa, or is it a copy? And there's the energy problem. Teleportation would require enormous amounts of energy, perhaps more than traveling normally, so it doesn't really solve the fundamental challenges. Another possibility is matter replication. If Santa could replicate presents on demand at each home, he wouldn't need to carry them. He could carry just the information needed to replicate them, or perhaps access a matter replicator remotely. But matter replication, like teleportation, raises questions about energy and feasibility. Creating matter from energy requires enormous amounts of energy. according to E equals mc squared. Replicating billions of presents would require energy equivalent to converting enormous amounts of mass to energy. So the theoretical solutions are interesting, but they don't really solve the fundamental problems. They either require even more energy, or they raise new problems, or they're purely theoretical with no evidence they're possible. The most practical solution remains multiple Santas, using advanced but potentially achievable technology. Fusion engines, advanced materials, AI navigation, regional workshops, coordination networks. This is still enormously challenging, but it's within the realm of what might be possible, with sufficient technological advancement. But even with multiple Santas and advanced technology, the challenge is profound. It would require technologies we haven't invented yet. It would require materials we haven't discovered yet. It would require capabilities we can only dream of. So what's the real answer? What would it actually take? Let's explore that final question. We've explored the challenges, we've explored the solutions, we've done the math. We've thought about physics, biology, engineering, and logistics. So what's the real answer? What would it actually take for Santa's sleigh to work? The honest answer is, it would take technologies and capabilities that don't yet exist, and may never exist. But that's not the whole story. The question isn't just about what's possible, it's about what would be needed, and what we can learn from exploring that question. Let's summarize what we've discovered. For one Santa to visit all 1.1 billion homes in one night, he would need to travel at about 300 kilometers per second, which is about 0.77% of the speed of light. This is thousands of times faster than sound, and would require enormous amounts of energy. The sleigh would need to travel in space, above the atmosphere, to avoid air resistance. It would need advanced propulsion, perhaps fusion, or antimatter engines. It would need materials stronger and lighter than anything we currently have. It would need navigation systems more precise than GPS. It would need computing power beyond our current capabilities. The energy requirements would be astronomical. Even with nuclear fusion, Santa would need fuel weighing hundreds of tons. The sleigh itself would weigh hundreds of tons. Accelerating such a massive object to such high speeds would require energy equivalent to what the entire world uses in a year. But with multiple Santas, the requirements become more manageable. With 24 Santas, each traveling at about 64 kilometers per second, using advanced propulsion and materials, the problem becomes difficult, but potentially achievable. Each Santa would need a sleigh with fusion engines, advanced materials, AI navigation, and access to a regional workshop. The logistics would still be enormous. Finding every home, planning routes, coordinating deliveries, managing presents. But with sufficient computing power and coordination, these problems might be solvable. So the real answer depends on how we approach the problem. With one Santa, it's essentially impossible, with any technology we can imagine. With multiple Santas and advanced technology, it becomes enormously difficult but potentially achievable. But what if we relaxed some assumptions? What if Santa only visited homes in certain regions? What if he only visited homes with chimneys? What if he only delivered to children who wrote letters? These changes would reduce the scale of the problem dramatically. If Santa only visited homes in developed countries, he'd need to visit about 300 million homes instead of 1.1 billion. That's still enormous, but more manageable. If he only visited homes with chimneys, he'd eliminate many modern homes, further reducing the number. If he only delivered to children who wrote letters, he'd reduce the number even more. But these changes would fundamentally alter the legend. The magic of Santa is that he visits every child, regardless of where they live, or whether they wrote a letter. Relaxing these assumptions makes the problem more solvable, but it also makes it less magical. But here's what's really interesting about this question. By exploring what would be needed, we've learned about physics, biology, engineering, and logistics. We've explored the limits of speed, the nature of flight, the capabilities of living things, and the challenges of large-scale operations. We've also learned something about problem solving. When faced with an impossible challenge, we can break it down into smaller pieces. We can explore alternative approaches, we can relax assumptions, we can divide the work. These strategies don't always solve the problem, but they help us understand it better. We've discovered that some problems can be made more manageable by dividing the work. We've discovered that advanced technology can push the limits of what's possible. We've discovered that even impossible challenges can teach us something about the possible. This principle applies beyond Santa's sleigh. When engineers design complex systems, they often break them into smaller subsystems. When scientists tackle difficult problems, they simplify assumptions. When businesses scale operations, they divide responsibilities. The strategy of division and coordination is fundamental to solving large-scale challenges. We've also learned about the limits of current technology. Our fastest aircraft travel at about Mach 3. Our most efficient engines convert about 40% of fuel energy to useful work. Our strongest materials have strength-to-weight ratios of about 1.5. These are impressive achievements, but they fall far short of what Santa's sleigh would need. So what would it actually take? It would take multiple Santas, advanced propulsion, advanced materials, AI navigation, regional workshops, coordination networks, and computing power beyond our current capabilities. It would take technologies we haven't invented yet, materials we haven't discovered yet, and capabilities we can only dream of. But more than that, it would require a fundamental shift in our understanding of physics, materials, science, and engineering. It would require breakthroughs comparable to the discovery of flight, the development of nuclear power, or the invention of the computer. These aren't incremental improvements. They're revolutionary changes. But more than that, it would take imagination. It would take the willingness to explore impossible questions. It would take the curiosity to understand what would be needed, even if it can't be done. And that's what makes this question so valuable. By exploring the impossible, we learn about the possible. By pushing against the limits, we understand where those limits are. By asking what would be needed, we discover what might be achievable. So the real answer isn't just a list of technologies. It's an exploration of limits, of possibilities, of what might be possible if we push hard enough. It's a journey through physics and engineering, through biology and logistics, through the impossible and the just maybe possible. And in that journey we've learned something profound. We've learned that even the most impossible challenges can be broken down into solvable pieces. We've learned that dividing the work can make problems more manageable. We've learned that advanced technology can push the limits of what's possible. But we've also learned that some challenges remain fundamentally impossible, at least with our current understanding of physics, and that's okay. The value isn't in finding a solution. The value is in exploring the question, in understanding what would be needed, in learning about the limits and possibilities of our universe. So what would it actually take for Santa's sleigh to work? It would take multiple Santas, advanced technology, enormous energy, and capabilities we can only dream of. But more than that, it would take the willingness to explore impossible questions, to push against limits, to imagine what might be possible. And in that exploration we've discovered something wonderful. We've discovered that even impossible questions can teach us something profound about the universe we live in, about the limits that shape it, and about the possibilities that exist within those limits. As we reach the end of this exploration, let's take a moment to appreciate what we've discovered. We started with a simple question: what would it actually take for Santa's sleigh to work? And we've journeyed through physics and engineering, through biology and logistics, through the impossible and the just maybe possible. We've calculated speeds and distances. We've explored flight and propulsion. We've examined reindeer biology and capabilities. We've thought about energy and materials. We've considered time zones and logistics. And we've discovered that the challenge is enormous, but not completely insurmountable. With multiple Santas, advanced technology and sufficient resources, the problem becomes difficult, but potentially achievable. It would require technologies we haven't invented yet, materials we haven't discovered yet, and capabilities we can only dream of. But it's not fundamentally impossible, and in exploring this question we've learned something profound about the universe. We've learned about the limits of speed and energy. We've learned about the nature of flight and propulsion. We've learned about the capabilities of living things and the challenges of large-scale operations. So whether Santa's sleigh could actually work isn't really the point. The point is the exploration, the journey through science and imagination, the discovery of what would be needed and what might be possible. And in that exploration, we found something wonderful. We found that even the most impossible challenges can be broken down into understandable pieces. We found that by asking what would be needed, we can learn something profound about the universe we live in. So sleep well, and dream of possibilities. Dream of multiple Santas, of advanced technology, of what might be possible if we push the limits. And remember, the magic isn't in the answer. The magic is in the question, in the exploration, in the wonder of discovering what would be needed. What we've discovered tonight is that even impossible questions can teach us something profound. By exploring Santa's sleigh, we've learned about the limits of speed and energy. We've learned about the nature of flight and propulsion. We've learned about the capabilities of living things and the challenges of large-scale operations. We've learned that some problems can be made more manageable by dividing the work. We've learned that advanced technology can push the limits of what's possible. But we've also learned that some challenges remain fundamentally impossible, at least with our current understanding of physics, and that's okay. The value isn't in finding a solution. The value is in exploring the question, in understanding what would be needed, in learning about the limits and possibilities of our universe. The legend of Santa Claus brings joy to millions of children every year. The science behind the legend, that brings understanding, it brings wonder. It brings appreciation for the incredible complexity of our universe, and for the limits that shape it. The story of Santa has evolved over centuries. The modern version, with flying reindeer and a sleigh, emerged in the 19th century. But the physics behind this legend? That's timeless. The laws of motion, the principles of flight, the limits of speed and energy. These don't change. They apply equally to Santa's sleigh and to a commercial airliner. By exploring the impossible, we learn about the possible. What we've discovered tonight is that even impossible questions can teach us something profound. By exploring Santa's sleigh, we've learned about the limits of speed and energy. We've learned about the nature of flight and propulsion. We've learned about the capabilities of living things and the challenges of large-scale operations. We've learned that some problems can be made more manageable by dividing the work. We've learned that advanced technology can push the limits of what's possible. But we've also learned that some challenges remain fundamentally impossible, at least with our current understanding of physics. And that's okay. The value isn't in finding a solution. The value is in exploring the question, in understanding what would be needed, in learning about the limits and possibilities of our universe. So as you drift off to sleep, think about what we've discovered. Think about the numbers, the calculations, the physics. Think about what would be needed, and what might be possible. Think about multiple Santas working together, about advanced technology pushing limits, about what might be achievable if we push hard enough. And remember, even impossible questions can teach us something profound about the universe we live in. The magic of Santa isn't in the physics, it's in the wonder, in the joy, in the belief that something impossible might just be possible. And in exploring that impossibility, we've discovered something wonderful, that even the most impossible challenges can teach us something profound about the universe we live in, about the limits that shape it, and about the possibilities that exist within those limits. Good night, and may your dreams be filled with wonder and possibility.